Alpha-2 antagonistic actions and mirtazapine. Alpha-2 antagonism is another way to enhance the release of monoamines. Norepinephrine turns off its own release by interacting with presynaptic alpha-2 autoreceptors on noradrenergic neurons. Therefore, when an alpha-2 antagonist is administered, norepinephrine can no longer turn off its own release, and noradrenergic neurons are thus disinhibited, such as those in raphe and in the cortex. And as seen in previous chapters, norepinephrine can turn off serotonin release as well by interacting with presynaptic alpha-2 heteroreceptors on serotonergic neurons. Alpha-2 antagonists block norepinephrine from turning off serotonin release as well. Because alpha-2 heteroreceptors on serotonin axon terminals are blocked even in the presence of norepinephrine. Therefore, serotonin neurons become disinhibited and serotonin release is enhanced. Thus, alpha-2 antagonists acting at serotonin axon terminals cut the brake cable of noradrenergic inhibition, in which norepinephrine steps on the brake to prevent 5-HT release. That's the second mechanism in which norepinephrine neurons from locus coeruleus intervene the cell bodies of serotonergic neurons in the midbrain raphe and stimulate serotonin release from serotonin axon terminals via postsynaptic alpha-1 receptors on the serotonin cell bodies. Thus, when alpha-2 antagonist causes norepinephrine release in the raphe, this also causes stimulation of postsynaptic alpha-1 receptors on serotonin cell bodies in the raphe, thereby provoking more serotonin release from the downstream axon terminals such as those in the cortex. This is like stepping on the serotonin accelerator. Thus, alpha-2 antagonists both cut the brake cables and step on the accelerator to facilitate serotonin release. These two mechanisms, that is, the monoamine transport blockade and alpha-2 antagonism, are synergistic. For this reason, the alpha-2 antagonist mirtazapine is often combined with SNRIs for treatment of cases that do not respond to SNRIs alone. This combination is sometimes called the California rocket fuel. Mirtazapine does not block any monoamine transporter. However, it not only blocks alpha-2 receptors but has additional potent antagonistic actions upon 5-HT2A, 2C, 3 and H1 histaminic receptors. Two other alpha-2 antagonists that are marketed as antidepressants are mianserine, that is marketed worldwide except in US, and cetiptaline, that is marketed only in Japan. 5-HT2C antagonistic actions theoretically contribute to the antidepressant effects of mirtazapine and mianserine as well. The H1 antihistaminic actions of mirtazapine and mianserine should theoretically relieve insomnia at night and improve anxiety during the day, but could also cause drowsiness during the day. The combined 5-HT2C and H1 antagonistic properties of mirtazapine could also cause weight gain. 5-HT3 receptors are localized in the chemoreceptor trigger zone of the brainstem, where they mediate nausea and vomiting, and in the gastrointestinal tract, where they mediate nausea, vomiting, as well as bowel motility. Blocking these receptors can therefore protect against serotonin-induced GIT side effects. They also regulate the release of various neurotransmitters, especially norepinephrine and acetylcholine. As we know, serotonin acting at 5-HT3 receptors reduces the release of these neurotransmitters, so blocking 5-HT3 receptors can cause disinhibition of these. Thus, agents such as mirtazapine with 5-HT3 antagonistic properties should enhance the release of various neurotransmitters. Potent 5-HT3 antagonism is also one of the 5 multimodal pharmacological actions of an experimental antidepressant vortioxetine in late stages of clinical trials.